All right, so for 45, they give us the function y is equal to the fifth root of x minus 3 raised to the fourth times the quantity x squared plus 1 all over 2x plus 5 raised to the third. All right, so now we need to take the derivative of this. Fifth root is kind of confusing, but we know one little trick we could use. That's the same as raising all that stuff to the 1/5, right? So if that's the trick I'm going to use, I got x to the third, x minus 3, not plus 3. Is that what it is in the book? Yeah. Raised to the fourth times x squared plus 1 all over 2x plus 5 raised to the third. Now we could use, we could, there's a lot of ways you could handle this. You could expand the top, in other words, multiply those out, FOIL it, and expand the bottom, FOIL it, and you'll get like a really long polynomial. You'll get like a 6th degree polynomial in the top and like a 3rd degree polynomial in the bottom, and just use the power rule. But really, it's you'd have to use like the quotient rule and the chain rule, and it's complicated. But this is on logs, so what we're going to do is we're going to say the natural log of y is equal to all this stuff, x minus 3 raised to the fourth times the quantity x squared plus 1 all over 2x plus 5 raised to the third power. And we're going to take the natural log of that, and that whole thing's raised to the 1/5. Now, the reason we did that is, what does the natural log, what are the properties of logs allow us to do with that 1/5 power?
Throw it to the front.
Throw it to the front. So I'm going to have the natural log of y is equal to 1/5 the natural log of all this stuff. Okay? And you might say to yourself, well, Mr. Adams, I don't see how this is any easier. Well, it's not. It is actually, but it's not super duper easy. So I'm going to take this whole thing and take the derivative with respect to x. So on this end, I get 1 over y dy dx, because that's what the derivative of that is. 1/5 is a constant multiplier, so we'll leave that to the front, and then we're going to take the derivative of all this stuff. So we're going to take the derivative of all this stuff, but that's the natural log of all this stuff on the inside. Now, before I take the derivative, there's a property of natural logs that I could use to make it easier. That property, I'll write it in red and show it on the screen. If I have the natural log of m times n, that's the same as the natural log of m plus the natural log of n. If I have the natural log of m divided by n, that's the same as the natural log of m minus the natural log of n. Okay? So I can clean up this fraction thing by applying that property. In other words, I could say I'm going to take the derivative of the natural log of x minus 3 raised to the 4th power plus, because I'm multiplying here, right? Plus the natural log of x squared plus 1, right? Minus the natural log of 2x plus 5 raised to the 3. Now what that allows me to do is a couple of things. I'm still not quite ready to take the derivative because I want to clean up this natural log business, because then when I go to take the derivative, it'll be a lot easier. So I've got the 1/5 in the front, and then I'm going to take the derivative of all this stuff with respect to x. But now this, because it's a natural log, I could toss that 4 to the front, and I say the natural log of x minus 3. So I say 4 times the natural log of x minus 3. Does that make sense? I'm going to pause right there. I don't want to go too fast. Anybody have any questions about what I've done up to this point? All right. So I'm going to do that with anything that has a power. And so then this becomes the natural log of x squared plus 1 minus 3, the natural log of 2x plus 3. I ran out of some room there. Okay? Now, the benefit in that is that when I go to take the derivative, I've got y, 1 over y dy dx is equal to the 1/5 that's tossed to the front. When I take the derivative for each one of these, what happens is I get 4 over the natural log of u, which is going to be the stuff on the inside. And so, in other words, it'll be the natural log of u, and then you tack on the derivative. Well, what's the natural log of x minus 3? Or, I mean, what's the derivative of x minus 3? It's just 1. So I'm going to write them in so you guys see it. Then plus, this is just going to be 1 over, oh, it's not, it's this. Let me write it down. Remember that when I have the natural log of u, if I take the derivative of the natural log of u, it's just 1 over u times the derivative. Right? You guys remember that?
Yeah.
Does that make sense? So when I go to take the derivative of all this stuff here, when I take the derivative of this, the 4 gets tossed to the front, and that's times 1 over u, which is this stuff here. Then you tack on the derivative of this on the back end. So here I have 1 over this stuff, which is going to be, well, I'll write it in a different color so you can see, x squared plus 1, but then I got to remember to tack on the derivative of x squared plus 1, which is 2x, right? All over 1. And then for this one, I'm going to say minus 3 all over 2x plus 5. Is it 5? Yeah. But then we have to tack on the derivative of 2x plus 5, which is 2. Okay? And then we go from there. So we're almost done. So now, if I clean this up a little bit, I get 1 over y dy dx is equal to 1/5 times the quantity 4 over x minus 3 plus 2x over x squared plus 1 minus, oh wait, yeah, and then this is 6 over 2x plus 5, right?
Instead of negative 3 on the first one? Or?
Yeah, because this was a negative here, and so that's a negative. So negative 3 times 2 is negative 6. Good question.
In the first.
Yeah, well, originally that was on the bottom. So where that comes from is that we use this property of the natural logs. Because this we're dividing by the 2x plus 5, then we would subtract the natural log of 2x plus 5. And the 3 comes from the fact that it was raised to the 3rd power. So we use the property of logs to toss that 3 to the front, and that's how we get this 3 times the natural log of 2x plus 5.
I meant in 4 over x minus 3.
This here?
Yeah.
Yeah, that's a 3.
No, is it supposed to be minus?
Yeah, originally it was minus, right?
It was plus. Oh, wait, you're right.
I think somewhere down there, like at this step I wrote it as a plus and I scribbled it, made it a minus. Yeah, I apologize. So, okay. So now we're almost done. I'm going to push that 1/5 through. And so I've got 1 over y dy dx is equal to 1/5 times all this stuff, which is really 4 times the quantity. See, now I wrote a plus sign. Like that, plus 2x all over 5 times x squared plus 1 minus 6 over 2x plus 5, and then we can multiply that by 5. So I just multiplied everything by 1/5. You guys with me? We're almost done. Well, what am I solving for? What am I doing? I want dy dx, right? So I've got to multiply all this stuff by what? Y. So I get dy dx is equal to y times all this stuff. Now you could probably skip a step or two if you want to do the stuff like this with your homework. Mr. Adams is writing out every step so you know where the numbers are coming from and what I'm doing, hopefully. Now, do I want it in terms of y or do I want it in terms of x?
You gotta close the parentheses.
Oh yeah. Do I want it in terms of y or do I want it in terms of x?
X.
So watch this. I'm going to take this and I'm going to plug in what y was, right? Remember all this stuff a long, long time ago, about an hour ago? This stuff here, I'm going to plug that in for my y. So here we go. Are you guys ready? Actually, I'm going to plug in the original one, which would be dy dx is equal to the fifth root of x minus 3 raised to the fourth power times the quantity x squared plus 1 all over the quantity 2x plus 5 raised to the third power. That's the y term, right?
Oh my god.
What's that got to be multiplied by?
All that other stuff.
All this other stuff. 4 over 5 times the quantity x minus 3 plus 2x all over x squared plus 1 minus 6 all over 5 times 2x plus 5. And this is our answer. Any questions?
I thought you were going to make us plug it in.
Yeah, now what, yeah, so that's kind of funny, right? Like, we did all that work. What does that represent? That's the equation that represents the slope of the tangent line at any x value of the original function y equals the fifth root of all this stuff.
That's way over my head.
I quit.
Way.
You give up? It's not over your head, but most of it's just algebra, right?
Does it get worse?
Over my head
Makes sense
since
when
we
you're
started.
doing it. Is that coffee? We have to like.
It's over yet.
Yeah, I
Is there
still can't
something
s-
dripping from the ceiling?
No,
Still
what's
can't
that
spell
purple
calculus.
thing?
Well, it's
Like,
like-
Water's getting-
Yeah, but why is water staying around if it's